Hi, welcome to the Olympiad geometry. Let's continue our study. Before we start, if you think this video is helpful, please click the like button, comment, share, and subscribe the channel. Today we're going to talk about the geometry treasure, continue our study on the parallel lines. So we're going to use the theorem we already proved before, the side splitting theorem and the definite proportion to prove the parallel line properties. Okay, so the first thing is that if MN is in parallel with AB, then the area of triangle MAB equals to the area of triangle NAB. So let's see this one. We can do this. We can just assume that the triangle area of MAB is larger than the triangle area of NAB. Right, you can assume this. And then we get the conclusion that MN does not parallel to AB, right? Which means if MN is in parallel with AB, we have that triangle area of MAB equals to the triangle area of NAB. Right, we can do this. So think about that triangle area of MAB is larger than the triangle area of NAB, which means AB is here, MN is here. We can just find a point P on the line MN, right? We can find this point P. Which means we can set MN to MP equals to be lambda. And we know that lambda is less than 1, right? And based on the definite proportion, we know that the area of triangle NAB equals to lambda times area of triangle PAB plus 1 minus lambda times the area of triangle MAB, right? That's what we already learned based on the definite proportion. And for this one, we can just assume, or we can just not assume, we can let lambda equals to 1 minus the area of triangle NAB to the area of triangle MAB. Right, because the area of triangle NAB is less than the area of triangle MAB, so this is a number less than 1. And we use 1 minus this number, so this lambda is less than 1, larger than 0. So this is valid, right? We can always find this point, or we can always find this setting, this lambda. And we let lambda equal to this, means we find a point P satisfy this this equation, right? And if we put this lambda back to this equation, then we get the triangle area of SNAB equals to lambda, which is this one, 1 minus SNAB to the area of triangle MAB times the area of triangle PAB, and plus 1 minus lambda, which is NAB to MAB times MAB, right? And from here, these two cancels. And we have the area of triangle NAB here, we have area of triangle NAB here, which means 0 equals to 1 minus NAB to MAB times PAB, right? And this is valid because this number, this is lambda. Lambda less than 1 but larger than 0. So that means the area of triangle PAB equals to 0, which means P is a intersection point of MN and AB. Right? P is the intersection point of MN and AB. Okay, that means MN and AB are not in parallel, which means if MN is in parallel with AB, then we get the area of triangle MAB equals to the area of triangle NAB. Okay? So for the second half, we see here if the triangle area MAB equals to the triangle NAB area, then MN is in parallel with AB. We can just have the similar method, which is we use that we set MN is in parallel with MN isn't. So here MN isn't in parallel with AB, right? And then we want to get the conclusion that triangle MAB area does not equal to triangle NAB area, which means triangle MAB area equals to triangle NAB area. We have to have MN in parallel with AB. Right? That's what we want to do here. So let's just see if MN is not in parallel with AB, then we know that MN and AB has a intersection point, right? Let's call this point P here. So we have MN AB here, right? Then we know that the area of triangle MAB to the area of triangle NAB equals to MP to NP, right? This is what we learn from the set splitting theorem, right? We have this one, the area of triangle MAB to the area of triangle NAB equals to MP to NP, which means MP is larger than NP. It's larger than 1, right? That means the triangle area MAB triangle area does not equal to the area of triangle NAB, which means if triangle area MAB equals to triangle area NAB, then MN is in parallel with AB, right? That's for the second half. Okay, let's see the third one. If line L1 is in parallel with L2 is in parallel with L3, line AC and DF intersect L1, L2, L3 on ABC and DEF respectively, then we have this. Okay, so basically it's saying we have 3 lines. L1, L2, L3 are in parallel, right? And we know that ABC is here, and we know that DEF are here. L1, L2, L3. Okay, A, B, C, and D, E, F. We just know these three lines are in parallel. We want to prove that AB to BC equals to DE to EF. Now we think about what we learned, what we just learned, right? If AD is in parallel with BE, that means the area of triangle ABE equals to the area of triangle DBE, right? So we connect AE here, we connect BD here. So we get AB to, wait, let me do this. AB to BC equals to the area of triangle ABE to the area of triangle BCE, right? That is AB to BC. And because the area of triangle ABE equals to the area of triangle BDE, right? Because L1 is in parallel with L2, that's what we just learned. So that equals to the area of triangle BDE, right? Because AB equals to BDE. And the area of triangle BCE equals to the area of triangle BFE, right? So now we turn it to be the area of triangle BDE to the area of triangle BFE, which equals to DE to EF. Okay, we just prove it based on the theorem we just learned. Okay, so let's see the next one. In triangle ABC, triangle ABC, DF is in parallel with BC. DF meets AB on D, AC on F. This is DF, right? Then AD to DB equals to AF to FC, which is simple, right? We just draw this line here. The A here is reused for the D here, right? Okay, so we just prove it. Let's see the next one. P is a point out of line AB. There exists and only exists one line passing through P and in parallel with AB. Okay, so for this problem, we first need to prove that this parallel line is existing, which means we have to find a method that can find the parallel line. We can just use what we learned, right? We learned that if there exists this parallel line, and we have AB here, we have P here. If exists this parallel line, then we know the any point on this parallel line form with AB to a triangle, and that area equals to the area of triangle PAB, which means we just need to find another triangle which has the same area of triangle PAB while it has the edge AB. Then we find it, right? Okay, then this is very simple. So we can just find the midpoint of PB, right? And find the, call it M. And we find AM here. And we find MQ equals to AM here. Now we check about the area of triangle QAB. right? So we know this area equals to, MA equals to MQ, right? That makes the area of triangle MAB equals to the area of triangle MQB. And we already know that M is a midpoint of PB. So the area of triangle MAB also equals to the area of triangle PAM, which means the area of triangle PAB equals to twice of the area of triangle MAB equals to the area of triangle QAB, right? That means PQ is in parallel with AB. This is what we just learned. Okay, now we find this parallel line, meaning that we find a way to find the parallel line that passing through the point P while in parallel with AB. Okay? And we want to prove that this parallel line is only one that passing through P. So we can assume that there are like more than one parallel lines passing through P while in parallel with AB. So another line must intersect BQ. Right, let's call it Q prime. Then we can just connect AQ prime here. So based on that PQ prime is also in parallel with AB, then we know that triangle area of Q prime AB equals to the triangle area of PAB. But we know that triangle area PAB equals to the triangle area QAB, which is not correct or say invalid with the figure, right? Because Q prime is another point on BQ. The triangle area of QAB does not equal to the triangle area of Q prime AB, which means this assumption that we have another parallel line passing through P other than PQ is invalid, which means the parallel line that passing through P is PQ, right? It's the only one. Okay, that's this property, right? Let's talk about the next one. If AB is in parallel with CD, CD in parallel with PQ, then AB is in parallel with PQ. So basically we have line AB here, and we know that AB is in parallel with CD. And we also know that CD is in parallel with PQ. We want to prove that AB is in parallel with PQ. Remember that what we can do is to just, because PQ is any point on the third line, right? We can just define it. We can just define it. So how do we define it? We first find another line that intersect with these three lines. So we call it ACP here. And we draw another line starting from the point P, right? So we find the point M and point B. And also we connect AM, we find the point Q. We connect BQ, we find point D. right? It changes nothing. It just give us some particular point we can discuss. So we already know that AB is in parallel with CD, and CD is in parallel with PQ, right? So because AB is in parallel with CD, so we know that the area of triangle ACB equals to the area of triangle DAB, right? Remember that we want to still use, if we want to prove that AB is in parallel with PQ, we have to find the triangle of APQ that equals to the triangle PBQ, right? So let's see this way. AB is in parallel with CD. Wait, let me see. CD is in parallel with PQ. So we actually have, because AB is in parallel with CD, which means we can have the triangle CAB equals to the area of triangle DAB, right? But in this way, it's difficult to relate these two, the triangle CAB and triangle DAB, to the area of triangle APQ, right? So let's just think about another way. We want to prove, let's just reversely derive it, right? Basically, what we want is that to find the area of triangle APQ equals to the area of triangle BPQ, right? And for these two triangles, we already know that they have the common area of triangle MPQ, which means we want to find the proof that the area of triangle APM equals to the area of triangle BMQ. Right, we want to find that the proof this area equals to this area. And because CD is in parallel with AB, P is a point. P is not just on this line; it's a point out of AB and CD, right? So we know that PC to AC equals to PM to MB, right? PC to AC equals to PM to MB, right? You got it, PM to MB. Okay, and because B is a point out of CD and PQ, right? So we know that PM to MB equals to QD to DB, right? That's all what we just learned. So we get that PC to AC equals to QD to DB. Actually, we can already use, we don't have to go to this way, right? We can already use what we learned here. Because PC to CA equals to QD to DB, that means L1, L2, L3 are in parallel. right, using this one. Okay, so that's this one. And let's see the last one. Two parallel lines intersect with a third line. Okay, two lines, not necessarily parallel. Okay, two lines intersect with a third line. If corresponding angles are equal, two lines are in parallel. Okay, this is a kind of difficult if we don't introduce other method, but let's just use what we learned so far to try to prove it. Basically, it's saying that we have two lines here, and we have both lines intersect with the third line, and we already know that the corresponding angles are equal, right? So this angle equals to this angle. These two angles are equal. Now we want to prove that these two lines are in parallel, right? Okay, these two angles are equal, and we want to prove that these two lines are in parallel, which can be done by this way. So think about, we find the midpoint of this PQ here, right? We're assuming that this line has, so basically we want to prove these two lines are in parallel, but let's just assume these two lines are not in parallel, which means they would have an intersection point. Let's assume the intersection point is far, far away here. It's called point X, right? And now we can rotate the whole figure by 180 degrees. You can rotate this whole figure by 180 degrees, which means that point P go to the point Q, and point Q goes to the point P. While this line, because this angle keeps the same, right? That means this line converts to here, and this line, the line 2, shifted to the line L1, right? And what about this intersection point? It goes 180 degrees to here. Right? But all the figures are identical, which means this point exists already there, right? It exists already, it's been there, which means these two lines have two intersection points. Right? That means impossible because these 2 points define a line. So in that case, these two lines must be in parallel, right? Because they cannot have 2 intersection points. Okay, so that's all we learn about the parallel lines. That's a very, very basic stuff, but we use a hard way, we use a difficult way to explain it. I think it's very useful because it's the basic stuff is always not that easy, right? Because it's kind of philosophical stuff. It's not pure math. Okay, I hope you like this one. See you in next video. Thank you.